Thank you all for joining us today. We are on our second lecture of our lecture series for the fall. This fall we are, this whole year UW-Whitewater is celebrating 150 years. So we're doing lots of things to celebrate such a milestone for us. And we thought it would be a good idea here for the lecture series to highlight some of our brilliant faculty members who really make Whitewater what it is. So yeah, you'll get to see some of our best for the best, right? So
no pressure here.
Yeah, no pressure, none. But I think you'll agree with me after today. So if you do have a cell phone or anything that makes noise, if you would silence it at this time. Also, if you're not a resident of Fairhaven, and if you'd like to receive our mailings, so we mail out our schedule of lectures a few weeks in advance of the first lecture. I know a lot of you see it in the newspapers and stuff too, but if you'd like to get on our mailing list, just come and talk to me and I'll put you on our mailing list and make sure that you get one in the mail for next semester. But let's go ahead and get started. We'll get started in the back with the recording too. They wanted me to give them a heads up. So let's go ahead and get started. I'm Carrie Bourne. I'm from the Office of Continuing Education at UW-Whitewater, and we host the Fairhaven Lecture Series each semester. And again, this semester we're celebrating 150 years of UW-Whitewater by highlighting some of our faculty and staff and the research and teaching they do. And I'll go ahead and introduce today's speaker. Professor Robert Benjamin received a bachelor's degree in mathematics and physics from Carleton College and master's and PhD in astronomy from the University of Texas at Austin. His research focuses on the structure of the Milky Way galaxy and the physics of interstellar and intergalactic gas. Please welcome Bob Benjamin.
Well, thank you. It's a pleasure to be here. And sort of in the spirit of this campus celebrating its 150th anniversary, I wanted to give a talk that was partly history. And so you'll notice I've been starting off with showing some home movies here. This is actually a home movie from 1950. It was taken at the dedication of a telescope in Ann Arbor, Michigan, the Curtis Eber Doust telescope. And at the time, in 1950, you had a collection of some of the most preeminent astronomers in the world who gathered together and talked about the frontier of astronomy at the time. And the frontier in 1950 was the structure of the Milky Way galaxy. I'm going to tell you a little bit about the history of that, and a particularly important year, 1951. And then I'm going to fast forward to this year, because this year has actually seen probably one of the most important advances in our understanding of the structure of our own Milky Way galaxy, since 1951. So let me go ahead and start the talk here. If you were paying attention in the beginning, you saw there was a period in the slide where you saw a gathering of people at the front. That was their conference photo. So they were all sort of standing in front of the observatory to have their picture taken. So from the front row, Fred Miller, Carl Hennies, who actually ended up working in the NASA space program, Harlow Shapley, let me circle a few. Probably the most important one that I wanted to highlight here is the Walter Baade, who was an astronomer, actually a German astronomer who worked in California during World War II. Being German, he wasn't really allowed to be part of the war effort, and being an astronomer, he had the opportunity to be in Los Angeles when they blacked out the entire city. And so he was able to use the telescope there in California to great advantage because all of Los Angeles down below went black. He did a tremendous amount of pioneering research from Mount Wilson Observatory. And one of the things he did at this talk, at this meeting in 1950, is he laid out the course by which astronomers might figure out the spiral structure of our Milky Way. So if you know anything about galaxies, you might know that some of them have this spiral pattern. I'll show you examples shortly. But we, being embedded inside our own galaxy, found it very hard to work out, to find really convincing evidence that we could see the spiral pattern in the Milky Way. And so what Baade had done is in 1950, he had taken the very first photographic plates of the nearby galaxy Andromeda using what's called H-alpha filter. So he was basically using a small wavelength of red light that's emitted by gaseous hot nebulae called H2 regions. And he said, he looked at that image of the Andromeda and said, you know what really traces spiral arms is H2 regions. And so if you were going to try to find the spiral structure of the Milky Way galaxy, what you should do is you should look out into the sky and find those nebulae, those H2 regions, and then measure their distances and put them on a map and see if you can see any evidence of a spiral. And so in 1950, he actually made that sort of prediction. He also was aware that we were going to be limited in how far across the galaxy we could see, because it turns out that in between the stars there's gas and dust that blocks our view, so you can't see too far in optical wavelengths. But you should be far enough, he argued, to see parts of the spiral arms. Right next to him is Harlow Shapley, a famous American astronomer. He was based at Harvard College Observatory. And Harlow Shapley was most famous for figuring out the size of the Milky Way. So until Harlow Shapley came along, it was really unclear the shape and the size of our own galaxy. When you look out in the sky at night and see all those stars, every single one of those stars that you can see is part of our own Milky Way galaxy. And then the nearest galaxy beyond the Milky Way is so faint and so far away that it's only a faint smudge on the sky. So every star you see is part of our own galaxy, including our sun. And so what Shapley did is he was actually the very first person to measure the size of that distribution by using globular clusters, these clusters of stars spherically distributed around the Milky Way. He figured out that the Milky Way was probably, from us to the center of the galaxy, he estimated at the time was 100,000 light years. This just blew the previous estimates out of the water. People realized, oh my gosh, the Milky Way is so huge. Actually, subsequent to that work, a Wisconsin astronomer realized that Shapley had made a mistake in those calculations. That's Joel Stebbins. He was a UW-Madison professor for many years. He realized he corrected Shapley's mistake and he shrunk the galaxy by about 30%. And so he got famous for basically shrinking the galaxy back down a bit. And so then also showing up in this picture, and the person I'm going to focus on a lot, is Bill Morgan. Bill Morgan was an astronomer who, although he was affiliated with the University of Chicago, did almost all of his work here in Wisconsin. He was working at Yerkes Observatory, which is in Williams Bay. And if you haven't had the opportunity to Williams Bay to see Yerkes, you need to go right away. Because Yerkes is basically being shut down by the University of Chicago. Its ultimate future is uncertain. There is a foundation that's being formed called Friends of Yerkes Foundation, where they're trying to gather together the money to create sort of an endowment to keep the telescope open for public tours and for educational outreach. But right now, that's not a done deal. And it's scheduled to shut down after, gosh, I don't know how many, almost a century of operation, more than a century of operation. It's due to be shut down in October. And so it makes sense for the University of Chicago. It's no longer a cutting-edge telescope, but it is actually the largest refractor that is a lens-based telescope in the world. It was the limit of that technology. After that telescope down in Yerkes, they went to mirrors as the fundamental technology for telescopes. But Bill Morgan worked there, and Bill Morgan was the person who made the breakthrough in 1951 that I'm going to describe. So before I do that, though, I'm just going to give a little bit of overview of galaxies. So if you don't know what a galaxy is, let me explain. Then I'll talk about the 1951 and the 20th century effort to map the structure of our galaxy, which I've already described to you a little bit. And then talk about what's been going on this year, thanks to a European mission that I'll explain shortly. By the way, I copied some of these slides over at the wrong date, so I apologize for that. So if you've how many of you have had the opportunity to see the Milky Way at night? Raise your hand. Okay. If you go to a very dark site, okay, outside of the city lights, particularly this time of year, a little earlier, maybe July or August, and look towards the south, you'll see this milky band across the sky. And what you're seeing there is the collected amount of starlight of all those stars in that direction that are basically tracing out this disk of stars that we're surrounded by in all directions. Okay, well, along the disk. So if you go to Oregon, this is a photographic picture. You can see that band crossing across the sky. This is also similar to our view. The center of the galaxy doesn't get very far from the horizon. Okay, so they're in the south. If you look sort of due south in the summer, if you look due south and you see this band towards the south is where you will find the center of the Milky Way galaxy. So when you're looking in that direction, you're looking at the center of our galaxy. And if you basically follow this 180 degrees, you'll be looking at the anti-center. You'll be looking away from the center of the galaxy. So the galaxy is we're in it, right? And you can see this. And if you wanted to get a better view of the galactic plane, this band, this Milky, by the way, it's called the Milky Way because the collected starlight looks milky, right? It's like a milky streak across the sky. So if this is a picture taken from Thailand, so further south in latitude, and you can see the center of the galaxy now. There's a bigger distance to get down to the horizon. And the best place to view the Milky Way galaxy, if you really want a spectacular view, is down in the southern hemisphere. Chile is the northern part of Chile is great. This is actually a picture taken directly above, directly overhead, between a bunch of telescopes in Chile with a fisheye lens, showing the galactic plane sort of spanning across the sky. So then the center of the galaxy would be directly above you, okay? And so it would be right here. And it was not lost on astronomers that when you look at this band of the Milky Way, and then you look at other galaxies that are out in space, galaxies can be oriented in any way. You know, they can be sort of facing towards you or sort of edge on. And if you look at the ones that are edge on, okay, and compare the ones the way they look to the way our own Milky Way galaxy looks like. This is an example of an edge-on galaxy, a very tiny thing in the sky. But if I blow it up and lay it across, it looks sort of similar. You know, we are in a galaxy that we view edge on, okay? And that's part of the challenge of figuring out what does our galaxy look like, because we can't get outside it. Even at the fastest speed of the fastest NASA probe, it would take 1 million years for that probe to get high enough above the galaxy to get a picture looking down. So the only way we can figure out what the galaxy looks like from the outside is through collecting data and then trying to analyze that data to get the outside picture. And that's part of what my career has been about. So galaxies, this just shows you several examples of spiral galaxies. So you can see, you know, these are not all the same looking, right? And so you have some that have very prominent what are called bars. These are bands of starlight that sort of cut through the center. Actually, let's see, another one here is this very famous one. So what's happening in these galaxies is stars, rather than going in circular orbits, go in sort of long, skinny orbits, at least in the inner parts. And those collection of those long, skinny orbits adds up to a band across the galaxy called a bar. But some galaxies are not barred. This one doesn't have any evidence of bar. Some have very nicely defined spiral arms, like this one. Some have very, very sort of patchy, just little pieces of spirals, right? And which one do we live in? I mean, that's been one of the driving questions of understanding the structure of the Milky Way. By mass, galaxies are 9% stars, 1% interstellar gas, and 90% dark matter, which is a sort of embarrassing situation to be in. We know from observing its gravitational effects that if we look at the way stars orbit in a galaxy, we can see that there must be mass there that's not emitting light. If our understanding of gravity is correct, then there's a form of matter that we are not able to detect using electromagnetic radiation. By function, what galaxies do is they convert gas into stars, and understanding how galaxies do this is one of the key goals of astrophysics. So this, through many, many decades of work, is an artist's representation of the Milky Way that I actually helped develop. It's turned out to be very popular, far more popular than I could have possibly imagined. Which means that every time I look at this, all I see are the flaws. But this is an artist's representation of the Milky Way based on data, and it's holding up, you know, pretty well over the last decade. But there are definitely some fixes to be made, which I'll describe. But in this picture, the sun is basically, well, I mentioned that the stars in the center go around in those elliptic orbits. That's why you get the bars. But if you go to the position of the sun, which I'll blink it for a second, you see a yellow dot at the bottom of the screen. Okay, so that shows where the sun is in this artist picture. And so from the sun to the center of the galaxy is 24,000 light years. Okay, it takes 24,000 years, actually closer to 27,000, for light to get from the center of the galaxy out to us. And our sun goes in roughly a circular orbit around the center of the galaxy. And so that's sort of the orbit of our sun. And if you think of each time the sun goes around the center of the galaxy as a galactic year, a galactic year is about 250 million of our years. Okay? So in other words, in the time it takes the sun to go around the center of the galaxy, our Earth will have gone around the sun 250 million times. Okay, and the Earth formed about 4.5 billion years ago, we think, along with the sun. So on that scale, the Earth is about 18 galactic years old. Okay? So in other words, our Earth, since forming, has made about 18 trips around the center of the galaxy. And so our sun is now, our planet, our solar system, I guess, is now ready to vote. And so just to give you a sense of the scale, the time scales that we're talking about here in astronomy, I mean, it turns out 1 million years in astronomy is not a very long time. But on Earth, you know, you can think of what was happening in the last time the Earth went around the center of the galaxy. So in the 17th time around the galaxy, going into the 18th time, we started off with a mass extinction, the biggest mass extinction on Earth that wiped out 96% of all species. Okay, that was the Permian to Triassic period. And so then the Triassic period, the geological period, where you had a supercontinent on Earth, okay, was basically lasted from here. And then there was another major extinction event. So this is all happening in our last galactic year, where 80% of all species on Earth were wiped out. That actually left the door open for the dinosaurs. Okay, so then the dinosaurs were stomping around for another fraction through the Jurassic period and into the Cretaceous period. Okay, and then at the end of the Cretaceous period, many of you may know that the dinosaurs were thought to have been wiped out by another extinction event, another presumably meteor that hit the Earth. In the Yucatan, I think. That wiped out 76% of all species on Earth, okay? And that left the door open for the mammals, okay? And so basically, mammals and eventually us were sort of the dominant life form on the Earth for the last quarter of the 17th or the 18th time around the center of the galaxy. So that just sort of gives you a sense of the scale of the times we're talking about. By the way, I should mention that, of course, over that time, the galaxy itself would be changing. So the bar would be developing, everything would be rotating in this picture. Actually, one of my goals is to create a version of this artist picture that shows how the galaxy changes over time, just as an outreach kind of picture. So at any rate, I'm going to skip through this. So let's go back to 1951. How did we come up with this picture, or how did we start to find this picture? I'm going to start 540 days before the announcement of spiral structure. I mentioned that Walter Baade was the one who described how you might do this in that meeting in 1950 in Ann Arbor. And basically he explains, of one thing we can be certain, on account of the heavy obscuration of the plane, we will at best get only a glimpse of short pieces of spiral arms. And one guess that we can probably safely make that our sun is located in a spiral arm, although that's not entirely clear now, is indicated by some evidence. I know this argument will not overly impress you and that you would like to see an arm or a piece of it demonstrated ad oculus, meaning it should be obvious to the eye when you look at the data that there's a spiral arm. So would I. So that's what Walter Baade said. And he gave the idea to Bill Morgan. This is actually a picture I found on Getty Images. It's a remarkable picture because it has some of the most famous astronomers all together in one picture in December 1st, 1951. Yes?
The man on the second from the right is my father, Frank Stromgren.
Oh my goodness.
1951.
You came in 1951?
He started being a director of your piece in 1951, January 1st.
Oh, I'm going to talk to you afterwards. I was so excited to find this picture because, first of all, it's a collection of some of the most famous astronomers in 20th century astronomy. Many of them are associated with the University of Chicago. Chandrasekhar, Subbarayan Chandrasekhar, Bill Morgan, who worked on spiral structure, Gerard Kuiper, who you may have heard something in the solar system called the Kuiper Belt, which is a collection of like dwarf planets and things in the outer solar system. Ben Stromgren, who hopefully I will hear more about very soon, who worked on the properties of nebulae, and Jan Oort, who was a famous Dutch astronomer of the time. The reason they were gathered together is that many of them were associated with Yerkes, but Oort was visiting in advance of the American Astronomical Society meeting that was going to be held on December 26, 1951 in Cleveland. And Oort had just launched the Dutch program to try to map the Milky Way in hydrogen gas. They were using radio waves, and he had made the first detection of hydrogen gas, but yet had not made a map. At this moment, Bill Morgan had actually made the very first map of spiral structure. And so Morgan showed Oort the map about a little less than a month before he presented it formally and officially for the first time. And so this is actually taken in 51. The day before the announcement of the discovery by Bill Morgan, he sat down with two other famous galactic astronomers, Priscilla and Bart Bok. These two met when, in 1927, when Priscilla was a professor at Smith College, and she came to Leiden as a visiting professor for an international astronomy meeting. Bart Bok was a graduate student who was assigned to basically be her guide and the guide of several other visitors to show them where are the hotels, how do you get to the meeting, and things like that. At the end of the week, he proposed to her. and she said, I don't think we should commit to that too quickly. She went back to the United States, but they continued to write, and he got himself transferred from his thesis in Leiden to finish his thesis work at Harvard College Observatory, so he could be close to her, and shortly after he did come to the United States, they were married. They worked as a team. They published a series of books, starting in 1941 all the way through 1981, summarizing the structure of the Milky Way galaxy. So they, actually, Bart Bok was sometimes known as Mr. Milky Way, or the man who sold the Milky Way. And the day before Bill Morgan announced the discovery, he actually sat these two down on his bed in the dorm room. The astronomers were housed in a dorm room in Case University in Cleveland. And he described the whole discovery in advance and let them know. Bart Bok was, pleased but also disappointed. He had also been trying to map out the spiral arm. So he realized afterwards he was barking up the wrong tree. He was using the wrong type of star that didn't show spiral arms as clearly as Bill Morgan's pictured it. But Bart Bok was the first person to ask a question in the presentation. The presentation in 1951 was actually the merging of three different efforts. The first effort was to find these H2 regions, these ionized nebulae. And so that was done using a camera that they had in the Yerkes Observatory. That camera was actually built as a projector. They were going to project stars on a dome to train pilots during World War II. They didn't use it as a projector. They actually, and then they realized, well, if you just reverse it, we can put it outside, and then light from the sky hits a mirror and then can be directed into a camera. And so then they put a camera at the top of it and used it as an all-sky camera, as opposed to an all-sky projector. And so that was to use to find the H2 regions. Then they found stars associated with those nebulae, and what are called O and B stars. These are the hottest, most massive stars. Most of those were found and classified at Yerkes, but some were also found at Warner-Swayze Observatory. And then you had to correct the starlight for the dust. There was dust in between the stars, and so if you wanted to get the distance to the star, you had to account for the fact that if there was dust, it could cause the star to dim more than you expected just because of distance, right? The further away a star is, the dimmer it will appear. But if you put dust, that also makes a star look dimmer. And so you have to figure out how much dust there might be. And so those dust corrections actually came from Washburn Observatory on Madison campus. So the original discovery of spiral structure was very much a Wisconsin discovery based on data from Washburn Observatory and two different telescopes in Williams Bay here in Wisconsin. And so Morgan presented those results. He actually published it. He didn't actually publish the original discovery properly. He actually was sick and hospitalized that summer. And so by the time he published it, the final version that was actually published in a journal looked different than the presentation. But we have a record of the presentation he did in Cleveland because he took a board, pounded in a bunch of nails, okay, and put little cotton balls in them. And this band you see here and this band you see here were his spiral arms. So the first map of the spiral arms of the Milky Way was a board with nails in it. And that board is visible in the Adler Planetarium in Chicago. It's on loan from the So you can find that board. And then eventually Morgan, Whitford, and Code, both Al Whitford and Art Code were professors at UW-Madison, finally published a collection of these. So this is slightly revised from the board picture. But it provided the first evidence of spiral structure. So basically these are just the plots of the stars showing a band of stars, another band of stars, and another band, if you believe that's a band. There was a little bit of I think people were desperate to find spiral structures, so they were willing to believe it. And Morgan was hailed as a hero, and that we were often running. I wanted to mention, just as a sort of interesting sidelight, that that camera that started the whole process going. I was giving a talk about this discovery in Madison, and I thought, well, I'll mention all the Wisconsin connections because I was talking in Madison. And someone, Kyle Cudworth, who was the former director of Yerkes, who happened to be in the audience, he said, well, Bob, I don't know if you know this, but that camera that Bill Morgan used along with Don Osterbrock and Stuart Sharpless, that camera that they used to find the nebulae in the sky that they mapped out, that camera's here in this department. And I was like, what? And he says, yeah. And it turned out that the camera used to make this first sky image where they found the nebula had been borrowed by Art Code in 1952, and he never gave it back. So this is the camera seen in Yerkes, and then this is the camera with Art Code, and he took it down to South Africa and took all sky pictures. Remember I told you that the galactic planes were overhead in Chile, so he went down to South Africa, took all sky pictures from South Africa. And then, because I opened up my mouth, we went tracing down the camera, looking in closets and things, and found the camera in a closet. It had been for the past 60 years, 70 years, bouncing around from grad student offices to closets, and no one really knew what it was, but it didn't get thrown out. So the pack rats among you, you were justified. So the camera was saved, and now it's back at Yerkes Observatory after all this time. So it made it back thanks to this connection that Kyle and Jim Lattice, who's a historian at UW-Madison in astronomy, and I made together. So that sort of kicked off the race for spiral structure. So I mentioned that there was this. It turned out that the approach that Morgan took to map out the distances of these stars was limited because there's dust and gas in between the stars, and so you can only see out to a certain distance. Sort of be like, if you wanted to see the structure of a forest and you were in a fog, you would be limited as to how much of the forest you could see, right? On the other hand, radio waves produced by neutral gas, which is written here as H1, we call it H Roman numeral 1 for neutral gas, that produces radio waves and that penetrates through the gas. And so, although Americans were the first ones to detect these radio waves at Harvard College Observatory in March 1951, the Dutch did it in May 51, together with an Australian group. All three published together in September 51. Then Oort came over to the United States, met with Morgan, and then the spiral arms were announced in December of 1951. I Love Lucy premiered in 1951, and then after that, the first effort to really map the hydrogen gas was done in July 1952 to 53. The Morgan-Whitford Code map I showed you, remember I said Morgan was sick, and so that publication was delayed. That was published in May 53. The first symposium of astronomers to talk about this new beginning in mapping structure in Milky Way was June 53, and then the first sort of magnum opus of galactic astronomy, the Dutch effort to do a complete map, was published in May of 1954. So that was the beginning of our modern attempts to map the structure of the galaxy. I'm going to just mention how we do two different kinds of ways of mapping. The first and the most fundamental way you can measure distances in astronomy, the distance to a star, the distance to anything, is a property called parallax. Okay. So I'm going to actually have you demonstrate it. If everyone would just basically hold their finger in front of their face as far as your finger will go and line it up with this edge of the screen and close one eye. So do it with one eye closed. Now, keeping your finger in the same place, try switching to the other eye. And your finger should switch with respect to that, right? Now, do the same thing, but bring your finger in to halfway. So just bring it in halfway and then try one eye and then the other eye. And what you should see is that when the finger's closer, the shift is more, right? That's called parallax. And you can basically, and because the Earth goes around the sun, every 6 months we have a slightly different viewpoint on a star. And that distance across the solar system gives us a slight different viewpoint, which means that stars actually wiggle across the sky as the sun goes around its orbit, just the way your finger was wiggling back and forth. That's the gold standard in astronomy. There are no assumptions that you need to make in that. However, the angles that stars move, the stars are so far away that the angles are tiny. And so it requires incredibly precise measurement of star positions to measure parallaxes. So initially, until just recently, this was how far parallaxes would get you out in the galaxy. You could really only map the galaxy out to this white circle, okay? The method that Morgan used was what we call a standard candle method. He assumed that if we find a kind of star, like an O star, B star, and we know its true luminosity, how bright it really is, and we observe its observed brightness, and we correct for the dust, then we can assume that the reason it's dimmer than we expect is because it's a certain distance away. So we treat stars as standard candles of a fixed luminosity. So that was actually the Morgan approach. And the Morgan approach basically got you this far out in the galaxy, because if you went much further than this, you had too much dust. Okay? So Morgan was able to sort of see evidence of this spiral arm, and this spiral arm, and this spiral arm. But beyond that, there was very little evidence. And so from that point on, most of the evidence for spiral structure in Milky Way came from those radio telescopes, because those radio telescopes could actually detect the radio waves from gas on the far side of the galaxy, for instance. I'm not going to go into the details of that because that gets a little bit complicated, the technique that radio astronomers use to convert their measurements of the distance. They would measure a Doppler shift of hydrogen gas. Is the gas coming towards you or away from you? And there was a way of assuming that the gas rotated in a circle, you would convert that Doppler shift into a distance. So there were maps, and this artist picture is based in large part on the subsequent 30 or 40 years of trying to map the gas. So let's talk about 2018, because things changed in 2018 in a very substantial way. In 2018, it became possible to measure parallaxes with incredible precision that people have not been able to measure before. And so this basically now makes it possible to map parallaxes. You can map parallaxes fairly reliably out to this distance, which means you have very precise distances. And above and below the disk of the galaxy, where you don't have any dust, you can also push parallax measurements out to the far side of the galaxy. So in April 25th of this past year, the European Space Agency released their first catalog of parallaxes to 1.5 billion stars in the Milky Way. Now the Milky Way is roughly 400 billion stars, so that's a substantial fraction of stars, although many of them are more sort of on our side of the galaxy. And with those measurements of parallax, that you can just use geometry to get the distance. It's been a gold rush of astronomers trying to do this. So this is an artist picture of the telescope. It actually is not a photograph of it. It looks sort of like a pancake or a flying saucer. What it has is it has two telescopes basically mounted, fixed to be 90-degree angles. And so if you measure a star in one direction, you measure a star exactly 90 degrees, and then you shift the telescope, and then you can sort of gradually, by measuring the position of every star with every other star, create these measurements of the parallaxes. But the moment this data came out, by the way, it's an unusual European mission because they said, we're going to collect all this data, and then we're just going to give it free, to all astronomers simultaneously. In other words, there wasn't the normal thing. It was like, wait, before we give you the data, we have 11 things we want to do with it, okay? They actually the team very selflessly just gave the data to the world on 25th. So just to show you, the two things that it measured was parallaxes, which this is just showing a little movie of parallaxes. So as the Earth goes around the sun, and you have a slightly different vantage point, your line of sight lines up at different points on the sky, and so you can see a star wiggling back and forth, right? And so that's the parallax that Gaia measured. And the other thing it can measure is just the steady motion of stars across the sky. If you know anything of the constellations, you can see where stars are with respect to each other. over the centuries, over the millennia, those positions will change. So this is actually showing you over time, from the past into the future, how the Big Dipper looked and how the Big Dipper will look as you go into the future. And this is all because all of the stars in the galaxy are moving with respect to each other. So eventually you will see them shift on the sky. And although the motions are small, they're measurable. And so you can actually measure the wiggles of stars and the drifts of stars across the sky using this telescope.
What's the time sequence of it? If you look up.
Yeah, so let's see. So the time sequence here is, this is showing the year, so it's like we rushed through the 20th century just very quickly. So you can actually see how the time is evolving now. The European agency, and I realized, I hope I'm going to have to. This may be a little too loud. The Europeans released another sort of artist version of this. I'll show you this in a second. Yeah, there's a question.
Is this what the concept of the Mercury retrograding? Is that the parallax?
This is actually not related to that,
Okay.
but there is a similarity in the sense that trying to measure the motion of Mercury around the sun, again, requires very precise measurements. But this is actually precise measurements of stars outside the solar system. So hopefully, let's see if it's too loud. So this is actually another European Space Agency where they're just going to show a picture of the galaxy. And the first thing they're going to show is grossly exaggerated. But they say if you pick all the nearest stars and exaggerate their wiggles, their parallactic motion, so what stars are going to be doing is, you see them going in circles. What's really happening is the Earth is going in a circle, right, and changing the perspective of the suns, the nearby stars, right? And so you can see that Earth motion reflected in the positions of the nearby stars. Then what it'll show you, so this is the small wiggles associated with some of the bright stars that make up our nighttime constellations. Then what the movie's going to show is the motion of these stars, proper motion of just how they drift over the years, millennia, and centuries and millennia. So you can see all the constellations are going to sort of come apart over the coming millennia, and we'll have new constellations that we'll have to create. Okay, but the thing is, these measurements from a year-to-year basis are tiny, amazingly tiny. But the European mission has encountered all sorts of technical things. And so I mentioned that this is produced a gold rush in astronomy. This is just a listing of all the papers that have been published since April 25th. And actually, I stopped this count at July 10th. Okay, there's been at least another page of papers that have come out, where astronomers now, given accurate distances, can say all these things about stars in the galaxy that they weren't able to say before. I'm not going to have time to say everything about them, but I just wanted to sort of highlight. I'm going to mention a few, skip over a few slides, and just point out one. But we've learned things about stellar evolution that we didn't know before. In particular, the stars like the sun will basically puff off their outer layers and end up with what's called a white dwarf in the center. And so Gaia has given us a complete census of white dwarfs around the sun and measurements of their distances. We found, if you know of astronomy, you may have heard of something called the main sequence. There's a gap in it, as it turns out, which is very mysterious. I think the cool thing is, because you can measure the motions of stars, they have found 100 or so stars that are what are called hypervelocity. By knowing their distance and by knowing their motion across the sky, we actually now know that these stars are going so fast through the galaxy that they appear to have enough energy to basically zip out of the galaxy entirely. So basically, our galaxy is ejecting stars, and there is one particular hypervelocity star that looks like it's coming towards us from another galaxy. So that a nearby galaxy called the Large Magellanic Cloud. So that's come out recently. There's all sorts of information on new clusters of stars, including the demotion of a few clusters of recently been true. We see evidence that stars are sort of streaming and warping, and I'll get back to this last thing because I think it's very interesting. That about a few billion years ago, that the Milky Way swallowed another galaxy, and we can see evidence of it by seeing the weird motions of some of the stars in the inner Milky Way. They've measured the motion of things that orbit the Milky Way, stars that in nearby galaxies. And the thing I wanted to do with this data, it turns out there is a problem with the Gaia data set, which is stars that are too bright, they haven't been able to measure these positions accurately. In other words, it's too bright, it basically blows out the detector. And they need some more years of measurements to get the thing. Because what I really wanted to do was take Morgan's stars from 1951 and measure their distances with parallaxes and see if Morgan's map from 1951 holds up. And so I was all ready for that, and then it turns out that the data's not up to it. But with data release 3, which will come out in about 16 months, hopefully I can do that experiment. So we still don't know if Morgan got it exactly right. But I did want to say that one of the things that we see, if you look in the inner part of the Milky Way, you can find there's this collection of stars. The color scale here indicates that the center of the galaxy is here. This is probably plus or minus 60 degrees from here to here. And what we see are all of these stars in the inner part of the galaxy, and they're not rotating the same as most of the stars in the Milky Way. And they're not rotating in the same characteristic way. They're rotating more slowly, okay? And so this is taken as to be evidence that that the Milky Way is still digesting an old galaxy, which we know happens in other galaxies, but it's sort of interesting to prove it in the Milky Way. This was independently discovered by two groups, three groups. One group called it the blob, one group called it the sausage, and then the final group called it Gaia Enceladus. So there's still an argument in astronomy. It's like, do we call it Gaia Enceladus or do we call it the sausage? But it's clearly evidence that there's a grouping of stars in the Milky Way that rotate differently than all the rest of them. And it's taken as evidence that the Milky Way, another galaxy came in close to our Milky Way and got absorbed and swallowed it. And we basically took all of its stars, and you can see evidence of it from the way they orbit. By the way, in case you're wondering where Enceladus comes from, Enceladus is one of the offspring in Greek mythology of Gaia, the earth, and Uranus, the sky. So I like it because I like classical mythology.
What was the first name?
The first name was the Blob. So the first authors had called it the Blob, but it was almost simultaneous. That there were three groups that almost came out with simultaneous papers claiming to find the structure, and then now they all agree that it's the same thing. They just disagree on what we should call it. So I'm going to stop there. The last thing, I just want to end with a few things to remember. The things that you might want to know about the Milky Way is that we're strongly barred. That's something you can take to the bank. We know we have a bar. The galaxy, I would say, is the most like the Milky Way. I've picked out a Milky Way analog as my favorite. My favorite galaxy for possibly looking like the Milky Way might look like is NGC 3953. So it has a nice prominent bar. It has somewhat organized but slightly messy spiral structure. I think that would explain a lot about the history of astronomy. But we're a partially mapped spiral galaxy. We're a warped galaxy. I didn't talk about that, but the disk is not perfectly flat. And it's about 10 billion years old. The sun formed 4.5 million years and has made 18 galactic orbits. And if the two things hope you remember is that one is that spiral structure was discovered here in Wisconsin. You didn't know that. Hopefully you'll remember. And then the second thing is that there's this huge burst of excitement now because of the ability to measure parallax, which, as you saw, gives you a very precise measurement of distance. So that's it. Thank you very much.
We do have time for a few questions. Who has questions? Okay, let me get around to you.
At the beginning of your presentation, if I remember, you mentioned that the Milky Way galaxy is about 90% dark matter, and 9% gas?
It's about 9% stars, 1% gas,
Okay.
and 90% dark matter.
So what about all of the planets?
The planets would count in the star category.
But why aren't they relevant?
Well, it turns out that, even in our own solar system, I forget what fraction, the sun, by mass, the sun dominates over everything else in our solar system. If you add up the mass of all of the planets and all of the asteroids and everything, that's just a tiny, tiny fraction of the mass of the sun.
So you're concerned about mass?
Yeah, so by mass, if I do it by mass. If I do it by number, of course, there's one sun and zillions of little things going around it. But that would be, it's hard to know how to count all those. As
But
astronomers
we
have
know,
proven.
we know they're there though, don't we?
Oh yeah, we know that there's all those little pieces of material going around the solar system. And in fact, there's a congressional unfunded mandate that astronomers are supposed to find all of the potential Earth impacting meteors, asteroids, to make sure that we know where they are before they hit the Earth in the next extinction event. And so NASA actually does continue to try to fill out its catalog of these small things going around the sun.
Just call them small things.
Small things on an astronomical scale.
Okay, thank you.
Oh, sure.
Back in the good old days, there was something called ether, and that kind of got thrown away, and now we're back to black matter again. What is the difference between those two theories?
Oh, you've opened a can of worms there. So if you know anything about the history of astronomy, or history of physics, you may know that when people figured out that light was a wave, I mean, light, we know that they're called light waves. And there was a wave in what? You have waves in water, you have waves on a string, you have waves. So initially when they first realized that light was a wave, they said, well, light must be a wave in this medium that we'll call the ether. And so there was this long-standing expectation in physics that there must be some medium in which the light travels, and you could tell the difference. You could actually learn about the ether, for instance, by looking at how light goes this way compared to, say, crosswise if you're moving with respect to the ether. All the experiments to detect the ether failed, and it was quite a mystery until we realized that there is no ether. That the light waves are basically traveling in nothing. It's a property of the vacuum. So what you learned by paying attention to that is that sometimes we have an explanation for something, and yet we don't have the proof for it, right? It explains light waves if we believe in the ether, but we don't know what the ether is. Well, we are in a similar situation now in astronomy and astrophysics, is we can precisely measure the gravitational pull on things, and it appears that 90% of the pull comes from some kind of matter that we don't know, or our whole theory of gravity is wrong. And that maybe we need to modify our understanding of gravity. And there is a group of physicists, and one of them actually is a case, who very strongly push the idea that if you only modify the theory of gravity in certain ways, you can explain away the need for dark matter. The problem is that there are many tests for the existence of dark matter, and it's past all of them. So there does appear, there's many different ways to check to see if dark matter exists, and it's past all the checks. And the people that argue that it's our theory of gravity are getting pushed into a smaller and smaller corner in terms of how is it possible that we just don't understand gravity. But it's an excellent question, and I personally, I worry about that. It's like, if 90% of what I study is a form of on matter that I don't even know, that's a pretty bad state to be in.
Yeah.
Might the bar that we have in the center of the galaxy be affected by or formed by the collision with the other smaller galaxy that came through?
Absolutely. That's actually one of the questions about bars and galaxies. It seems like about 80% of spiral galaxies have bars. And in astronomy, we now know that if you can form a bar, you're likely to keep your bar in a galaxy. The question is what triggers a bar to form out of those nice circular orbits that we think a galaxy starts with. And so the standard assumptions are, well, maybe an interaction with a nearby galaxy triggers the bar formation. And actually, that has been suggested that with the sausage, blob, Gaia, and Celebes. I'll just call it all three, so I don't irritate anyone, since I think this is being filmed. So anyway, I think that the thing is that this could be a potential source of the bar, but there's many other kinds of interactions that Milky Way could have had. And there's also other ways to trigger a bar to form in the first place. So we don't know for sure.
I'll follow up on that. We anticipate what Andromeda will collide with our galaxy. Can we do some type of a program to show what might happen?
Oh, there have actually, yeah, so one thing I didn't mention, and actually the case for this has gotten even stronger because the Milky Way is sort of here, and then we can see the Andromeda galaxy, and we can now measure the proper motions of stars in Andromeda. that even though it's very far away, you can actually see the stars in this nearby galaxy both rotating around that galaxy and slightly moving across the sky. And so you can actually project how the other galaxy, the nearby Andromeda galaxy, is moving with respect to us. And it looks as if the Milky Way and the Andromeda galaxy are heading for a collision or a near collision. That's less Earth-shattering or galaxy-shattering than you might think, because galaxies are actually mostly empty space. The spacing between the stars is vast compared to the size of stars. So it would be like taking two basically handfuls of sand and throwing them through each other. You could see the sand basically pass through, but the gravitational forces would actually, in the stars, would actually warp the shape of both galaxies. That's projected to happen in about 5 billion years, according to the models. And that's also about the age of the sun. So as at the same time the sun is basically ending its normal lifetime and becoming a white dwarf, the Andromeda galaxy should be very big in our sky. So, it really will look like end times, I think. Yeah. We can show here and this question over here.
I was just going to ask, do you have a suggestion of some reading, books that a layperson, a non-astronomer, would enjoy reading?
Oh yeah. So let's see. On the history. Well, I have so many books, so I'm trying to. I mean, one this Milky Way specific is called Alchemy of the Heavens. I believe this is by Cameron Oswald. And Alchemy of the Heavens, and that has a lot of the history of the galaxy as a place where stars form. Less to do with what I'm talking about. The history of the structure of our galaxy is something I really want to write, because there's so many juicy stories here, including the intrigue, backstabbing, you name it, it's in this field. And I've been sort of finding out a lot of the secret things, because you take people out drinking and then you say, so who discovered this? And then you get the true story. But other than Alchemy of the Heavens, there is a Coming of Age in the Milky Way by Timothy Ferris, is another Milky Way-oriented one. And of course, there's a host of other books that are about other topics of astronomy that I could recommend maybe afterwards. But those two, Coming of Age in the Milky Way and Alchemy of the Heavens. Actually, there was another one, but it's just about William Herschel, so I think probably not. It's not just astronomy, but there's a good reason and stuff there.
Okay, I think with that we'll close the Q&A part. But if you have some additional questions for Professor Benjamin, please come and chat with him and join me in thanking him for this excellent lecture today. Thank you, everyone.